Welcome to Chapter 1 of Computational Chemistry of the Oxygen Evolution Reaction. Green hydrogen has a simple recipe. Put electricity into water, take hydrogen out. The chemistry has been understood for 2 centuries, the engineering is commercially deployed, and renewable electricity keeps getting cheaper. Yet the electricity bill for a kilogram of hydrogen stays stubbornly higher than thermodynamics says it needs to be, and most of the excess is spent at one electrode. That electrode is the anode, where the oxygen evolution reaction happens. This chapter explains why the reaction that produces the byproduct limits the whole device. Water electrolysis is one overall reaction driven by 2 half reactions at 2 separate electrodes. 2 water molecules become 2 hydrogen molecules and 1 oxygen molecule. The electrons do not travel through the water. They leave one electrode, go around an external circuit through the power supply, and arrive at the other. Ions carry the charge through the electrolyte to close the loop. At the cathode, we have the hydrogen evolution reaction. At the anode, the oxygen evolution reaction. The hydrogen is the product we want. The oxygen is the byproduct, and it is where the trouble lives. Write the halves separately, in the acidic convention, and the asymmetry appears immediately. Hydrogen evolution moves 2 electrons and forms 1 bond. 2 protons pick up 2 electrons and pair into hydrogen. There is essentially 1 intermediate, an adsorbed hydrogen atom, and therefore 1 binding energy to get right. Oxygen evolution moves 4 electrons and 4 protons and must build an oxygen-oxygen double bond from atoms that started on separate water molecules. Add the halves in a 2-to-1 ratio, and every proton and electron cancels, leaving the overall reaction. Nothing is invented in the bookkeeping. Why is 4 worse than merely twice as bad? Doing 4 transfers in one concerted event is not physically plausible on a surface, so the reaction proceeds through a sequence of steps, each moving 1 proton and 1 electron through surface-bound intermediates. Each additional coupled transfer is another place to lose energy. Every intermediate must be bound. Bound too weakly and the surface will not form it, bound too strongly and it will not let go. A designer facing hydrogen evolution tunes roughly 1 binding energy. A designer facing oxygen evolution must get 3 right simultaneously on the same site. An electrode potential is a control knob on the energy of electrons in the electrode. Making it more positive lowers their energy. Moving 1 electron across a potential difference changes its free energy by -E times U, and for a reaction moving n electrons, the free energy change equals -NFE, where F is the Faraday constant. Read that backwards. Water splitting is not spontaneous, so the potential you need exactly cancels its positive free energy. That is the standard equilibrium potential, 1.23 volts. Per electron, 1.23 electron volts. 4 electrons, 4.92. At exactly 1.23 volts, thermodynamics permits water splitting, and nothing happens at a useful rate. Equilibrium potentials say where a reaction stops being forbidden, not how fast it goes. To drive real current, you must apply more. The overpotential eta is the applied potential minus the equilibrium potential. The extra voltage a real electrode demands. It is the central figure of merit of this series. A practical cell pays an anode overpotential, a cathode overpotential, and ohmic losses. We focus on the anode because its term is typically the largest, and because a surface is something you can redesign. The economics follow from a conservation law, not a market forecast. Faraday's law says each mole of hydrogen needs exactly 2 moles of electrons, and a kilogram of hydrogen is a fixed number of moles. So the charge you must push per kilogram cannot be negotiated by any catalyst, any engineer, or any subsidy. Energy is charge times voltage, and the cell voltage is 1.23 plus eta. Since the charge is fixed, energy per kilogram is directly proportional to cell voltage. Every volt of overpotential is pure waste, paid on every single electron for the operating life of the plant. Here is the sweep. The overpotential values are illustrative teaching values chosen to span a plausible range. They are not measurements and are not attributed to any material. At 0 over potential, the cell needs 32.71 kilowatt-hours per kilogram of hydrogen. At half a volt, it needs 46.00, and the voltage efficiency has fallen from 100% to 71.1%. Every extra 0.10 volts costs 2.66 kilowatt-hours per kilogram at any starting point. We state no electricity prices. Multiply by whatever your own situation carries. Why spend a series on quantum chemistry rather than experiments? The experimental loop is slow, and the space of plausible oxide surfaces, dopants, terminations, and facets is combinatorially large. Computation can ask the deciding question before synthesis, because activity is governed largely by how strongly a surface binds the intermediates, and binding energies are computable for a surface nobody has made. Now the caveat. We model a flat, perfect, static facet with approximate solvent, while real catalysts have steps, kinks, defects, and restructure while operating. What we compute is a thermodynamic lower bound on difficulty, not a measured polarization curve. The code takes only the Faraday constant, the molar mass of hydrogen, and the 1.23-volt convention, and derives everything else. Running delta G equals NFE forward gives 237.4 kilojoules per mole of hydrogen, exactly where the standard Gibbs energy of forming liquid water sits. We did not look that up, we derived it. Then the slopes. 5 intervals, identical to 4 decimal places, with a spread of 10 to the minus 13. Floating point noise, not physics. Cutting the illustrative overpotential from half a volt to a quarter saves 6.65 kilowatt-hours per kilogram. Let us recap. Water electrolysis splits into 2 half reactions that are not equally hard. Hydrogen evolution moves 2 electrons through 1 intermediate. Oxygen evolution moves 4 through a chain of 3. An electrode potential is a knob on electron energies, and 1.23 volts is the thermodynamic price, worth 4.92 electron volts across a full turnover. Overpotential is the extra push a real electrode demands, and because Faraday's law fixes the charge, the energy cost is strictly linear. Computation earns its place by predicting binding before synthesis. Next, the computational hydrogen electrode.